Okay, hi everyone. So my talk, this is a presentation about my master's thesis on EGRAPHS' modulo theories. A lot of this talk is going to be for specifically the theory of AC. I will maybe talk a bit about why later, but so you can also think of this as EGRAPHS' modulo AC. So here's how I like to think of EGRAPHS. You can think of it as sort of three layers. The bottom layer sort of handles ground atomic equations. E1 is equal to E2, E2 is equal to E3, so we should figure out that E3 and E1 are equal. And then on top of that, we have congruence closure, which handles the non-atomic equations where we have function symbols. And then the top layer is equality saturation, which handles identities, which are universally quantified equations. And the way the top layer works is if we have some universally quantified equations, we try and look for instances. And if we find an instance, we might have to add the other side of the equation if it doesn't exist. And this is the thing that oh, sorry, it's a some toy that I stepped on. My apologies. And then we might have to add the other side. This is what blows up the graph. And so AC is a particularly notorious case of blowing up the graph because, and in particular, commutativity is fine. But if you see an associativity, we sort of have to generate this new E node potentially if it doesn't exist on one side of the equation. So I'm going to focus on A and C together. I'll talk about why not just A by itself a bit later. But AC is very common and it's a problem. So, and there's often AC, you often have AC plus other stuff, ACU abelian groups. So just some examples. Here's A plus B represented as an E-graph. Here's A plus B plus C represented as an E-graph and run to saturation under AC. And A plus B plus C plus D. And yeah, you see it gets bigger. Someone asked me if, when I have given this talk previously, someone asked me if these were hand generated, and hopefully you can figure out the answer based on this. This is some size 8 term, a small window of it, A plus B plus C plus D. Run to saturation under AC. So obviously it's an exponential explosion. There's 2 to the n E classes and n times 2 to the n E nodes across those E classes, I believe. I've gotten those combinatorics wrong before, but I think that's correct. So solutions or non-solutions that have been mentioned in the past. One non-solution is to fire rules less and less if they're used too many times. So if we run associativity 100 times, then we decrease its weight, try fire some other rules. And this isn't. So firstly, this doesn't help if you intend to run to saturation, which is what you have to do if you want to be guaranteed to find everything. And it can slow down finding the equations you want to find because maybe there's some necessary use of A and C that you're sort of, missing out on by, well, not temporarily missing out on using. So here's just sort of an example of the kind of reasoning we might want to do with AC, a very simple example. So we imagine some function that satisfies this identity. It's an affine function, if that means anything to you. But the upshot is if we have f of something plus f of something, we sort of merge that into one f, but we also get this extra constant on the outside, this plus 1. So we start with 3 f's added together. We should be able to do 2 merges to get this plus 2 constant on the outside. But to do this, we sort of need a few steps of associativity, depending on how we represent the starting term. And here's the online egglog demo. I quite like this graph because you see there's this, it's very hard to see at this scale, but it's generated the constant 2, but it hasn't really found where to put it. So it's sort of, spend most of its time just sort of reassociating and commuting the plus nodes. So SAT people have added theory-specific solvers and made very successful SMT solvers. So why can't we sort of handle AC in a specific way using this idea of theory-specific techniques rather than relying on the general, powerful, but potentially the slowest equality saturation? That's the motivation, at least as far as I can see, for the name EGRAPHS' modulo theories. It's a natural idea to consider working up to AC in your EGRAPH somehow. That's been thrown around for a while. Philip Zucker gave a very nice talk on it last year. But there's some problems with, there's some technical issues that need to be sort of ironed out to make this work properly. So here's an example of how we'd like it to work, right? We'd like to think of plus as variadic. So in our example of 3 f's added together, we just think of it like this. We don't have to worry about which way to associate it. And then we run that affine function identity a few times, and eventually we hit saturation like this. And the thing we wanted to find, a plus b plus c, variatically added together here, f applied to that, and then plus of that with 2, that's our desired term, represented in this very compact final graph, which is saturated on that rule for affine functions. So that's what we'd like to do, but there's sort of a gap in this thing, which we go back to an even simpler example. A plus b equals b, so here's a. If you add b to it, you get b. The arrows kind of point a bit weirdly, so, but if you add a to itself, you get c, and if you add c and b together, you get d, right? And so what we would like to show is that b, we can expand b into a plus b, we can expand this b again into a plus b, right? So we get a plus b. Then we reassociate and we collapse a plus a into c, and we collapse c plus b into d. So this is b should equal d, right? This is the chain of reasoning we would like to our EGRAPH to represent. But you sort of see that we're sort of stuck, right? There's no extra rules. We've sort of represented everything up to AC, but there's sort of, we've represented everything up to AC, but we've sort of missed this consequence of the theory of AC, which we should have merged this E-class and this E-class in this E-class. So just making the sort of E nodes work up to AC, just thinking on this variadic and commutative, we've lost the equational reasoning required to actually properly handle AC. So we have an E-graph closed under congruence, but it's missing the desired equation. So we could add back some saturation step, but that sort of unsolves the problem that we were trying to solve in the first place. We don't want to just blindly saturate, we want to do something more clever. So this is my contribution, although it's based on work that's existed previously. So what we want to do is we want to think of adding this AC closure thing in between as a sort of in-between layer. It's more complicated and more expensive than congruence closure, but it's sort of less expensive than the general procedure of equality saturation, which works for anything, but is sort of slow for AC in particular. And so the way that AC closure works, well, we sort of look to rewriting systems. And so if we think of an E-graph, we can think of it as a rewriting system, just like has been pointed out in previous talks. G of EA, G applied to EA gives us E1 if we call this class E1 and this class EA. You can read all these things off the graph, and there's a bunch of more complicated ones. And you see that, for example, H of EA and E2 rewrites to both E3, but it also rewrites to E4, right? And so the way E-graphs do congruence closure is they see that we've got something that rewrites to two different things. And this is a critical pair, so we can E3 and E4 are both equal to the same thing in the middle, right? If we ignore the direction of these rewrites and just think of them as equalities. So we conclude that E3 is equal to E4, and then we can resolve that critical pair by merging E3 and E4. That's how congruence closure works. So to do AC closure, we need to find AC critical pairs. So in our example, we had this sort of, these two central terms are equal up to, well, A, or more generally AC. And so from these two things being equal, we learn eventually that C plus B and A plus B are equal. And C plus B was also, we could continue this further, C plus B was also equal to a D on this side, and A plus B was equal to B on this side. So the way AC closure works is you find an AC critical pair, T1, with some term that doesn't have to exist in the E-graph, just some term that could rewrite in two ways. And then we take the equation that we find and orient it into a new AC rewrite rule, like this. And then we introduce the new rule with the old ones. And so there's actually some design choices here. So this is the way I've just described, I'll call it the side table approach. We don't store the plus nodes in the normal E-graph at all. We sort of have a side table of these AC rewriting rules where we have, some AC term rewrites to some other AC term. And so when you would go to add E1 plus E2 to the E-graph, you create a new rewrite rule like this for some fresh E3. And then when we find a sort of unit rewrite rule in the AC part, the AC table, we sort of feed that back into the original E-graph. The alternative approach is this sort of integrated idea where you think of plus nodes as any other E-graph node, but you look for critical pairs as some separate step, right? But this is a more integrated way to think of things. I didn't think too hard about this trade-off when I implemented it, but they should be equivalent, you might think, but there's sort of a non-obvious thing that you might miss if you went with option 1, the integrated approach. So the integrated approach, if we had some equation, we'd generate a new symbol E, so new E-class ID for them, and put them into those E-classes. And it's this approach is more eGraph-like, because we in normal eGraphs we always have rules that are like this. Some function applied to something goes to E, but we never have a rule that some function applied to something goes to some other function applied to something. So they're equivalent only if you pay attention, because in the side table approach, if we make some new rewrite, E1 plus E2 goes to E3, and we have some existing rule that has E1 and E2 in it, then we can compress this existing rule down like this, right? The E1 and E2 have been merged into E3 now. And so essentially our algorithm is equivalent to Buchberger's algorithm, a standard algorithm in computer algebra. And so if you the side table approach connects very nicely to the textbook Buchberger's algorithm. But to make the integrated method equivalent, we need to do some kind of destructive rewriting to do this compression step, right, of introducing existing rules with new rules that appear. And it's maybe a bit alien for us eGraph people to think of this sort of destructive rewriting step of compressing down existing E nodes, but yeah. So they are equivalent, but you have to be aware of this. Otherwise, you sort of get problems with explosion again. So some results. So I have an implementation of this. As some toy examples, I generated random identities. I don't think that's a very representative sample, maybe, but it's the best I have. And I ran to saturation, which for many identities it doesn't hit saturation because there's some infinite loop. But we compare handling AC either with our sort of modulo theory approach or just via AC saturation, just running ordinary saturation on AC identities. And then we measure the final size. I just added together basically every measure of size I could to make it as fair as possible. And here's the final graph. So you see that here's the size with AC completion, the modulo theories approach, versus the size with AC saturation, the sort of traditional approach. And you see that all these green dots under the line, that's where the AC completion is smaller than the AC saturation. I chose to measure size rather than performance because I don't think my implementation is very well tuned for performance. But I would like to eventually do some other forms of benchmarking to compare them. But you see that generally AC completion is going to be smaller than running to saturation under AC, and you can kind of see as it gets bigger and bigger, you sort of get more and more savings, right, than the sort of potentially exponential blow up you would have with ordinary equality saturation on AC. So AC closure is just a form of Buchberger's algorithm, a well-known algorithm from computer algebra. Lots of work has been done to optimize it, but unfortunately, the problem is fundamentally E-space complete. So solving this gap, as I put it, there's no magic wand to solve it. You still need to solve a hard problem in the sense that it is E-space complete. Obviously, we hope that we can do it fast enough in practice. Now, so we're moving on to the more general case. Filling the gap, as I've termed it, is exactly equivalent to a well-known problem in algebra, which is the word problem. So for just associativity, the word problem is undecidable, so we can just have some A closure step as a neat little package. We could maybe have an A closure step that we feed it some number of steps and it goes to that number of steps, but there's no guarantees that we'll ever reach the end. Some word problems are much better than the E-space thing we have for AC. So if you have inverses and you get polynomial time, and then once you can have some sort of nice things that include division and things, then we get the word problem can be done via Gaussian elimination, which is a very well studied problem that's not just polynomial time, but a small exponent in the polynomial. Buchberger's algorithm, there's a lot of variants you can make of the same basic idea to handle other things, idempotence, inverses, all that sort of thing. Indeed, so this basic idea of AC closure already goes back to the rewriting literature by, among others, Tawari and Kapur, who have given some sort of variants of this. So this particular thing is not new. It's more the application of this idea to the eGraph world, and in particular, I want to point out that this closure, AC closure or ACI closure, or whatever you want to do, is sort of fundamental to solving the problem in a complete way. Otherwise, you're sort of missing some of the power or missing some of the consequences of the theory you're trying to work with. Yeah, so just a couple of notes that I won't go too in depth into this, but there's the problem of matching modulo AC. This is the sort of thing I actually started on before realizing that there's this completeness issue of just working up to AC without doing this extra AC closure step. I'll kind of skip over this quite quickly, but you can think of matching as kind of like a rewriting problem, right? So you can think of, if this is our EGRAPH, for instance, we have this pattern, there's a way to think of the pattern as its own sort of weird rewrite system. And I mean, we don't even need to think of it as a rewrite system. It's just a relation. What we are doing is we're sort of interleaving the relations in a certain way. But thinking of it as a rewrite system, then matching is sort of resolving critical pairs, right? So this sort of thing is you'd have one branch which is like the eGraph relation, and one branch which is the match relation, and you sort of find a critical pair to get that. You annotate some E-class with some match state. And so hopefully, I hope, obviously I'm skimming over this quite a lot, but I hope that you can generalize this sort of setup to explain what AC matching should do, and explain, hopefully it terminates in the general case as well. So yeah, so that's tentative work that you can do AC matching in a hopefully always terminating way by orienting rules to handle what would otherwise be a potentially infinite match space. So I'll explain the infinite match space problem. This a plus 0 is equal to a. So if we wanted to match the pattern a plus x, well, x could be 0, or it could be 0 plus 0, because you can sort of feed this back into itself, reassociate, and then you get this, substitute this a here for a plus 0. You get a plus 0 plus 0, and then reassociate, and you can do this infinitely many times. So the space of matches is infinite, but hopefully with a sort of this rewriting approach, you can find some sort of finite minimal set of matches that kind of represent the entire space. And a brief discussion of future work. I mean, if we just want to match, for example, this pattern, there are a lot of ways you could match this against this term, a plus b plus c plus d. But probably, in this case, we might just be looking for any case where there's 4 things added together. So there's sort of a lot of redundancy in this space of matches as well. So one way to deal with this, just some trick that I've found in existing literature, we might have some ordering constraints. So we could say that the substitute of whatever is substitute for x has to be less than y, has to be less than z, and that sort of cuts down the potentially combinatorially big space of matches. Yeah. So yeah, I started working on essentially the matching problem here, and realized that without AC closure, egress modulo AC are not very useful, because you're sort of throwing away some of the consequences of the AC identities that you'd want to find. And yeah, so please look at my upcoming thesis for more details. I'm not sure how fleshed out the matching part will be, but the working modulo theories and this sort of word problem or AC closure idea is very well fleshed out. So yeah, thanks very much. And I've got plenty of time for questions. So.
I think I will have to ferry them to Sofia. Okay, so I will attempt to do that. So we have time for a couple brief questions before lunch.
Thank you for insightful presentation.
Keep it short because I'll have to repeat it. She cannot hear that.
Oh, so I speak like.
Just speak it,
Aha,
and I
sorry,
have to
sorry.
memorize it and then repeat
Okay.
it.
So, to my understanding, the Buchberger's algorithm can be built as just a specialization of Knut-Bendix algorithm to polynomial ring of a linear field. So I think the wording of using Buchberger's algorithm is too narrow here, I think. So is in exactly what sense do you refer to Buchberger's algorithm instead of Knut-Bendix algorithm?
Okay, thank you.
Yeah, sorry, if you could just repeat the full question. Yeah. Mhm. Yeah. Yeah, so, I mean, I guess there's a few things to point out. So the first thing is, it is a specialization of both Knuth-Bendix and Buchberger's. The first thing is that if we want to generalize to things beyond AC, if we want to work with polynomials, rings, that sort of thing, then the more general version of Buchberger's can handle that just fine. The other thing to note is that Buchberger's algorithm, as a specialization of Knuth-Bendix, always terminates, which is very nice property to have. So obviously you can think of the general notion of EGRAPHS' modulo theories where you have some general Knuth-Bendix thing, but that doesn't really give you anything in the sense that Knuth-Bendix is just solving the same problem that equality saturation is solving by sort of instantiating identities and so forth. So we're kind of looking for a nice terminating subset, and Buchberger's is one such subset that handles general polynomials, and even within that we can focus on AC, or if we are working with some rings or polynomials, we can use the bigger algorithm. I hope that makes it clear. Okay. Yeah. Thanks, everyone.